A Bronsted-Lowry acid is any species that can donate a proton, for example, hydrochloric acid in water. A Bronsted-Lowry base is any species that can accept a proton, for example, ammonia in water. Polyprotic describes any species that can either accept or donate a proton depending on what the chemical environment is, for example, water. And now we want to look at what happens when an acid and a base react to make salt and water. For example, hydrochloric acid and sodium hydroxide can make table salt, sodium chloride, and liquid water. Titration is a method of quantitative analysis in which a standard solution called the titrant is volumetrically added to a sample that is to be analyzed, the aliquot, until the reaction is complete. When the reaction is complete and the aliquot has been neutralized, we call this the endpoint. If the reactants are a strong acid and a strong base, the resulting neutralized solution will have a pH of exactly 7.00. This is actually a limiting excess problem. The number of moles of hydrogen ions that were in the original acid, the aliquot, must equal the number of moles of hydroxide ion that has been added from the base. When this occurs, this is called the equivalence point. For example, if we take a 15 milliliter aliquot of 0.1 molar hydrochloric acid, it will have an initial pH of exactly 1.0. It will take exactly 15 milliliters of 0.1 molar sodium hydroxide to reach the equivalence point. That is the point where the number of moles of H plus equals the number of moles of OH minus. When the volume of the titrant and aliquot are both 15 milliliters, the resultant volume is 30 mils of salty water, and since sodium ions and chloride ions are both pH neutral in water, the overall pH of this solution is now 7.00. If we consider simply the pure sodium hydroxide, concentration 0.1 molar, it would have a pH of 13.0. The initial pH of pure acid is 1, the final pH of pure base is 13, and the equivalence point pH is 7.0. The graph of this titration would appear to be an S-curve, flat at first, going through pH 7 at 15 milliliters of sodium hydroxide added, and topping out at a maximum pH of 13. For our second example, we're going to take 25 milliliters of hydrochloric acid of unknown concentration and titrate it to an equivalence point with 18 milliliters of standardized 0.5 molar sodium hydroxide. In this case, the hydrochloric acid is the aliquot and the sodium hydroxide is the titrant. The titrant will be added to the aliquot until the endpoint has been achieved, which will be indicated by a phenolphthalein endpoint. Again, our goal is to get the number of moles of H plus ion and number of moles of hydroxide ion exactly equal. When we do the math on this, we find out that the original hydrochloric acid had a concentration of 0.360 molarity. And at the equivalence point, we will have a pH of exactly 7.0. When the weak acid, hydrofluoric acid, is titrated with the strong base sodium hydroxide, we must take into account that hydrofluoric acid is a weak acid and requires a Ka calculation with an ice table. When the math is done on 0.5 molar hydrofluoric acid, we discover the initial pH is slightly higher at 1.88. The final pH, as before, depends only on the concentration of the strong base. Since the strong base will also be 0.5 molar, the final pH will be 13.70. However, the equivalence point pH depends on the strength of the conjugate base of the weak acid. The salty water contains sodium fluoride. Sodium is pH neutral in water. Since fluoride is weakly basic, therefore the equivalence point pH will be something above 7. Our initial pH 1.88, pH at equivalence point 7.0, and the final pH 13.70. When titrating a weak acid and a strong base, we form a buffer. Now, a buffer is simply the combination of any weak acid and its conjugate base. An ideal buffer is when the weak acid and conjugate bases are equimolar. Initially in my system, before any sodium hydroxide is added, we have 100% weak acid. When I've added my 10 mils of sodium hydroxide and reached the equivalence point, it's 100% conjugate base. At the midpoint, at the addition of 5 milliliters of sodium hydroxide, it's exactly 50-50 between weak acid and conjugate base, that is, between the hydrofluoric acid and the fluoride ion. At that point, we have formed an ideal buffer. Any point between 0 milliliters and 10 milliliters of sodium hydroxide added to my hydrofluoric acid will form a buffer region. The resulting graph of this titration will show an initial pH of 1.88, a very slopy buffer region, an equivalence point of greater than 7, and a final pH approaching 13.70. In the third example, we now use a polyprotic acid with a strong base. Notice from the balanced equation that I need 3 moles of sodium hydroxide for every 1 mole of phosphoric acid. Once again, the phosphoric acid is the aliquot, the sodium hydroxide is the titrant. But since phosphoric acid is triprotic, every 1 mole of phosphoric acid requires 3 moles of sodium hydroxide to pull off those 3 hydrogen ions. It is now evident why it is incorrect to say moles of acid equals moles of base at the equivalence point. More correctly, it's moles of hydrogen ions equals moles of hydroxide ions added at the equivalence point. When we do the calculation of 0.5 molar sodium hydroxide that has been standardized, requiring 36.26 milliliters to completely titrate 25 milliliters of phosphoric acid, we end up calculating an initial concentration of the acid, of the molecular acid, of 0.242 moles per liter.